Hi, this is Ryusuke Sugimoto from the University of Waterloo. In this video, I'll talk about our SIGGRAPH Asia 2024 Technical Communication Submission, Galerkin Method of Regularized Stokeslets for Procedural Fluid Flow with Control Curves. I worked on this project with Jeff Lait from Side Effects and Christopher Batty and Toshiya Hachisuka from the University of Waterloo. In this work, we introduce a volumetric incompressible flow design tool that lets users directly specify velocity, angular velocity, or both of them, along control curves. In these images, we use the spiral curve as the input and visualize the resulting velocity field by evaluating the velocities at several points on two planes in 3D. Using the incompressible velocity field, we can run particle simulations, for example. An incompressible flow is a velocity field where the divergence of the velocity is zero everywhere. When we follow an incompressible flow, the mass of fluid is conserved without any non-physical sinks or sources of fluid materials. There are mainly two classes of methods to design such an incompressible flow field today. The first one is the projection method. This approach projects an arbitrary vector field into an incompressible one. While projection is implemented as a part of many different fluid simulators, it requires the discretization of the domain, which can be tedious for artists to set up, and dependent on the spatial resolution, the result can exhibit large errors compared to the analytical solution. Also, this projection method can change the input vector field in an undesirable and unpredictable manner, making it difficult for users to achieve their intended flow. The second approach is the curl noise approach. Given the potential field, we construct the output vector field by taking the curl of it. Unlike projection, curl noise does not involve any discretization in its core mathematical formulation. While adding turbulent, incompressible noise to augment an already incompressible input velocity field is easy with curl noise, it remains highly unintuitive for users to specify an intermediate potential field whose curl would yield an intended incompressible flow. In contrast to these two approaches, our proposed Galerkin method of regularized Stokeslets takes control curves with velocities specified along them as its input. Then, it naturally extends the velocities from the control curves to the surrounding space. Our Galerkin method of regularized Stokeslets is an extension of a method called the Method of Regularized Stokeslets. We consider the Navier-Stokes equations the complex nonlinear equations that describe the behavior of fluids. We can simplify these complex equations into the Stokes equations, which are simple linear equations, by assuming that the velocity field is an incompressible, constant density, and viscosity dominant quasi-static flow. For such simple equations, we can get an analytical solution called the regularized Stokeslet under a concentrated force. Given the concentrated force at one point, we can get an incompressible velocity field induced by that. As we are dealing with linear equations, any superposition of regularized Stokeslets still satisfies the Stokes equations and is incompressible. So given concentrated forces at 2 points, we can get a more complex incompressible velocity field. We can consider adding more points to describe a more complex incompressible velocity field. Using the matrix notation, we can write the relationship as this. We can evaluate the unknown velocity u at any point inside the space by considering the effects of all point concentrated forces, where the matrix S relates the two quantities linearly. With this, we can compute the velocities given the forces at control points. But how do we specify the velocities at the control points instead? We take a two-step approach to this problem. First, given the target velocities at control points, we solve a linear system of equations to get the forces at the control points. Once we find the forces at the control points, we can evaluate the incompressible velocity field's value anywhere in the space. In our work, to improve the usability of the tool, we want to consider one specific scenario of designing an incompressible velocity field. which is the case when we want to get the velocity field that follows the input velocity along control curves. Even in such a case, if we use the method of regularized Stokeslets, it concentrates forces only at discrete, isolated points. Moreover, we only try to match the given velocities specified at those isolated points. For velocities to match the target velocities along control curves, this means that we need a large number of points. When the number of points increases, the size of the matrix S to be inverted increases, making the method impractical. Our Galerkin method of regularized Stokeslets aims to solve this problem by employing the Galerkin formulation. We still discretize the control curves as polylines and store information at their vertices, but we interpolate the forces along the polylines so the forces are more smoothly distributed along the control curves. Moreover, we also interpolate the target velocities along the control curves so the velocity would match the desired ones on average along control curves, rather than at discrete points. When we solve problems with our approach, we only need relatively small degrees of freedom, keeping the size of matrix S small enough. This makes our method computationally tractable without using complex computation acceleration techniques. When we compare the two approaches, when the curves have many vertices, the results are nearly identical as we expect. When the curves have a very coarse discretization with much fewer vertices, as in this scene, only our Galerkin version can respect the horizontal velocity at the horizontal arm. This is one example where our method is more useful. We also extended our method so users can specify the angular velocities instead or in addition to the velocities, inspired by a similar method for elasticity. In this simple example, we can see that the velocity vectors are rotating around the input curve when we use the angular velocity control. For 2D and 3D problems, the Stokeslets have different forms. For 2D problems, we need to use the 2D version to get an incompressible flow in 2D. With the 3D version, we can observe that the divergence at the center is non-zero in this 2D plane. We can also change the influence radius from the control curves by changing the value of a scalar parameter. We can use this property for better artistic control of the flow. Our method is shipped as a part of the VFX software Houdini, so you can try it by yourself today on your laptop. As a future work, supporting triangle elements to have free slip and no slip boundaries in the flow design would be useful. The computational cost increases significantly for such extensions, so we would need to look into computation acceleration methods such as the fast multipole method and some tailored preconditioners for the linear system solve. In summary, our Galerkin method of regularized Stokeslets is a volumetric incompressible flow design tool that lets users specify velocity along control curves. Our method is a modification to the method of regularized Stokeslets. We replace the points in the original method with polylines and use the Galerkin formulation. Our method is applicable to 2D and 3D problems, and as an extension, we support angular velocity control as well. Thank you very much for watching this video, and if you have any questions, drop me an email.